So we are starting chapter number 4, forces and Newton laws. All the Newton's laws are the base of the classical mechanics that we have been working on in this course. So far we have studied the motion and different quantities which define motion, right? We called it kinematics. Kinematics, we never discussed the force, that where does that motion come from. We did discuss the speed, how fast the object is going, how slow the object is going. We talked about acceleration, we talked about speeding up, slowing down, but we never talked about how this speeding or slowing down occurs. Obviously, there must be some force on the object which results in increase in the acceleration, velocity and change in acceleration, and there must be something, some external agent which causes the change in the velocity and produces acceleration. That agent, when that comes into play, we call it dynamics. Okay, and dynamics is based on forces, how the forces act on the objects. When they act on the objects, how the object is going to respond. There are 3 laws of Newton which were published in Mathematica, and these 3 laws basically they are like the everything to our classical mechanics. They are applied to large objects. So how large the object could be? It could be as big as our sun or planets. It could be as small as molecules. So we can apply these laws to very small objects. However, for the dimension, like atomic sizes, anyone has any idea about the size of an atom? 1 angstrom, 10 to the negative 10, it's incredibly small. So when we come to that dimension, or even smaller than that, which is the nucleus, that is about 10 to the negative 15 femtometer. That is so small. In that case, classical mechanics laws, they do not apply the way they usually do to the other objects. There the quantum mechanics come into play. So we will have different, but still these laws, they remain valid. We still use in quantum mechanics some few things are derived from some basics that we already know from the classical mechanics. So after you finish this course, there are few things that you should have in your mind very clearly. These Newton laws are one of them. All 3 laws. Okay, the first law that talks about the force, but that more talks about the natural state of the body. Let's get started. There are some review questions on this. The forces, we will go through those review questions as we go through the PowerPoint. The dynamics, when we talk about the study of the field of physics, where we talk about how forces affect the object. Okay, kinematics, when there is no description of the forces, but the dynamics, where we talk about the force. The basic definition of force is same as that if you had seen physics before, you might have seen this definition already. Push and pull on an object, which is a vector quantity. It does have a magnitude and the direction. The external forces are the outside forces that act on the body. You don't want to talk about the internal forces of the object. For example, if you have a car driving, there must be some external force on it. What's happening inside the car internally, that is not of your concern. When you're talking about the bottle full of water dropping, then you talk about just the force of gravity acting on it. You don't have to do with what are the molecular dynamics inside the water. Free body diagram, when we draw all the forces on the object. Okay, now that is going to be a very important thing that we learn in this chapter, is how do we draw the diagram. Okay, anything without the diagram is not acceptable. So how do we take care of these free body diagrams? As you look at the picture, you see that there is a lady standing in the center, and there are two girls, they are pushing on her. How can I tell it's pushing? It is a vector and it's towards the object, correct? So the vectors, this is how they help you to understand the direction of the force, because this for F1, if I talk about the force on the left hand side, since it is towards the lady in the center, that means it's pushing on her. The same is true for F2, which is pushing on her too. Now we don't need these people in the picture. We can take them out, make a free body diagram, and that free body diagram that turns out to be this way. Why do I have them replaced? No, it is still the same picture. The only thing we have done here is, this is a vertical vector. You can place it here. It doesn't matter how you place them, but this is acting upward. So we can put it on the origin. So that is the center point at which the force is applied, and F1 is applied in the right side. Can you find out the resultant force? Yes, no, maybe? We can. How? Very good. You can find out. You can find out because this is a simple situation where you have a right angle triangle. So by drawing a hypotenuse to this, you can solve for the magnitude of hypotenuse. That is going to be the resultant force, as you can see up there. Okay, so by putting F1 first, then F2 on the top of it, putting the head to tail rule, where F1 ends, you put F2 on the top of it and draw a resultant vector starting from the tail of F1 ending at the head of F2. That would be your F total. That F total magnitude should be given by the vector formula that we already know. Right? Can we find the angle too? Yes. Correct? So it's a right angle triangle. You can solve for the magnitude of the total force. You can also solve for the angle or the direction at which the force is applied. So these are different examples of forces. The one you saw before, these are two forces, and how do you take care of two forces? On this one, if you have a mass attached with a spring, you pull the spring to the right, there is one force that you are applying on it, okay, by pulling it to the right. And then as a result, there is another force which is acting in opposite direction. Do we know what that force is? Have you heard about it before? Do you know there is a force called restoring force? There is a force exists. What happens when you pull something springy? What happens when you let go? It comes back. How does it come back without a force? Because there is a force, right? Because of the change in the elasticity of the spring, there is a force which is called restoring force by Hooke's law. Okay, by Hooke's law is not something that we do in classical mechanics. If you don't want to write it down, that's completely fine. But you will learn about Hooke's law in physics too. It is because of the force which has produced, because you stretch it, there is molecules displaced. They want to come back to their original position. There is a restoring force applied on it, and that brings it back to its original position. It's very much possible if you have attached a mass with such spring, you let go, it can go up and down, like oscillate about its mean position. But that force would be responsible for the acceleration produced in the spring. Now these are some examples of forces. How do we draw, or how do we represent them in the form of the vectors? Directions are important for forces. Free body diagrams are important. So our main objective is going to be how do we put the free body diagram together when there are multiple objects and multiple forces involved. Newton gave his first law, which is a very common observation too. If there is no external force on the object, there will be no change in velocity. If I leave this book here, I come back for my Friday class, Monday class, several weeks, and if nobody has moved this book from the table, I must be able to see this book on the table. Why it didn't go anywhere? Because it cannot go anywhere on its own. There must be some external force which will change its position. When it changes its position, it can change its velocity. However, does it mean that the object at rest is the one which follows Newton's first law and the moving object does not? There are a few questions I'm going to write on the board. Does it mean net force is 0? Does it mean net force is 0 if the object is not moving? Okay. Great enough, but there is some force. Small. Okay. Compared to the weight of the object. So for example, let me ask you.
Like if you pushed on that book, but you didn't push it hard enough to move it, there's still force on it, but it's not overcoming the force of friction that's on the book.
Yeah, but that just tell me there is a net force on it, but the object stays at rest, there will not be any acceleration. But does it mean that is the force applied by me? That is external. But just by looking at the book, is there any force acting on it? Yeah. Is there any force acting on you? Yeah. But how are you still sitting up? Chair. Thank God. It's there. Right? So the book is constantly pushing on the table. Okay, so if I have to draw the forces on the example you gave me, that is external force, right? That makes sense. That is correct example, but that applies to a different situation, that when there is external force. Internally, if I have something on the table, the gravity force acts downward. This is what you just told me. There is a gravitational force. Is there any other name for this force? Weight force. The force with which the earth pulls on you, that is your weight. So the weight acts downward. As a result, since it's pushing on the table, there would be an opposite force equal to this force of gravity. And how do we know it's equal? Because the book is not moving. Okay, if any of the force changes, the book will move. If I connect something like a piece of string with it and start pulling it upward, it will move because I have some extra force to go with it. But as long as it is in contact with it, they must have balanced each other. You notice I put this the name here, N, okay, this is a very unique force. It's called normal force. Normal force, we will discuss and do a lot of problems related to normal force. Normal force that comes from the objects in contact. This is not a friction force. Keep that in mind. Okay? It's not trying to oppose the motion. It comes as a result of the objects in contact pushing on each other. It is electrostatic in nature. As a result of charges, attraction or repulsion, there is some sort of force generated which acts in opposite direction, and that comes from pushing on some object as a result of the contact. And it's not stopping the motion, it's not opposing the motion, it's not friction. It acts exactly perpendicular to any object. It's called normal force because it acts perpendicular to any point. Okay? So, for example, if I want to talk about the normal force on this binder, that is going to be perpendicular to this. If I want to talk about the normal force to this surface, it's going to be perpendicular to this here. So that goes with the surface of the object under consideration. Normal force acts opposite. It's always acts perpendicular to the surface. If I have a surface which is inclined and I put a book up there, where do you think the normal force is going to be? Should it be here, 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 or here? So there is an inclined plane. Instead of keeping the book on the flat surface, I have put it on the inclined plane. Which vector do you think represents the direction of normal force? 1, 2, 3, 4. None. I don't know. I don't want to answer this question. Or it's everywhere. Normal force is perpendicular to the surface. 3. Yes. 3 is the correct answer. This is the correct answer. Okay, so you have to look at the surface and then figure out which direction the normal force is going to be. Now this is a picture from your book. 2 people pushing on a child in the cart, and this picture is in fact for the putting the forces together and draw a free body diagram in leading you to the point where forces are responsible for the motion. So these 2 people act on this child, F1 and F2. I hope you all can see it. It's very small picture. F1 and F2 is the forces exerted by these 2 people on that child, and there is a friction force acting in opposite direction. So if you don't understand why friction in the opposite way, it's okay so far, because we have not done the friction yet. So you will not see the problems which will include friction. You will see them as a part of the example. But as soon as you introduce friction, then we bring the friction in and then we solve the friction with the problem. Friction is acting in opposite direction. You see that the weight of the child and the cart is downward, which is the weight force. Normal force is upward, and it is accelerated to the right side. Right? So putting the diagrams together, the total net force is in this direction, and the acceleration is in the same direction too. Is there any acceleration vertically? Is the child going up or down? No wings there. It's not going up or down. It's only going forward. What does that mean? All the forces vertically, they have balanced each other. Just like the book on the table, they have balanced each other. Weight has balanced the normal force. That's why it's not moving in this direction. So only leftover force is the force applied by these two ladies on the cart, and these forces add up and the child is accelerated. Oh, I think these are just the pictures. So here comes the second law of motion.